Hello, this is a video lecture that is going to focus on a component of factor analysis, which will actually be something we call deriving factors. So the underlying idea here is that we have a bunch of variables and we want to reduce those variables to underlying, we want to understand the underlying structure of those variables which relate to each other. The ones that relate to each other will each represent a factor. So the question is, how do we do that and how many is appropriate? So within the process of factor analysis, this is like right in the middle, we have loaded up our data into a data set, and now it's time to try to figure out how many factors we'll actually have. To first understand this, a little bit of background information is probably helpful regarding variance and variance within variables that we have. So variance is often thought of as having three separate components. Common variance would be the variance that is shared between variables. So if two variables are correlated together, they have shared variance. So actually, if say for instance, two variables are correlated at 0.50, you square that, and that would be the amount of shared variance that they would have. So they would share 0.25 variance with each other, amount of variance with each other in that particular case. And that would be the common variance. So it's the variance shared or accounted for between variables. And this would be the commonality or the grouped or shared variance that they have. Another part of variance, one of the part of total variance is something called specific variance. So this would be variability within a variable that cannot be explained by any other variable. It is unique only to the variable that you're looking at. That would be called specific variance. So we have common variance, which is shared with others, and we have specific variance, which can't be explained by other variables. It's unique to the specific variable you are investigating. The final and last category of where variance comes from is error. So anything that can't be explained by another variable, anything that is not unique specifically to the variable at hand, is lumped into this error category. And so that's kind of what we're looking at there. Total variance then would be the sum or combination of common variance, specific variable variance, and then error variance. So there'll be two different types of factor analysis that use the concepts of variance to complete its analysis. Common factor analysis and then principal component analysis. So common factor analysis primarily focuses on the common variance that is shared between variables in order to come up with the factors or the groupings of variables that we're going to look at. Principal component analysis, or component analysis for short, considers all the variance together. And actually, component analysis is the type of analysis that is used more often than any other. Okay, so principal component analysis then is good for making predictions. It's good for setting a minimal number of factors. Again, it considers the total variance. So when we think of all the variance, all the three types of variance, common, specific, and error, it would focus on total variance together. It does not necessarily minimize error variance, but it assumes it is small. Common factor analysis. So the common factor again would consider shared or common variance as opposed to total variance. So this might be better for exploratory work as opposed to for prediction types of work. But we, again, principal component analysis is most often what is used. The third type of factor analysis method would be maximum likelihood estimation, MLE. So MLE is very similar to principal component analysis. Again, when we have, in this case, it's interesting, MLE is used sporadically, and when we're only using one factor or we're using one factor to estimate. This is not common, so this is uncommon to use to try to specify one factor. So MLE is not something we do quite as often, but PCA typically is. When you look at your software, oftentimes you'll be asked to choose what type of analysis you want to use. So if you're using SPSS or a software program and if there's a dialog box, you have options available to you. When it asks for your method, this is what it's asking for. It's asking for, do you want a principal components or some other type of common factor analysis, or do you want to use an MLE or what you want? So just use the drop down box and select what you want. Again, principal component analysis is going to be common. The other thing in this particular box that you have a choice of is an option here where you can specify how many factors or how many underlying dimensions you want to identify. So that's another thing that we can do. We can let the software program choose that number for us, or we can specify that number as well. And that's something that we'll talk about here in just a second. Just remember, as we're looking at the method component, PCA is used most often. And the dirty little truth here is that when you start having a large sample size, most of the results are going to be very, very, very similar to each other, regardless of whether you use a common factor analysis or a principal component analysis. So, you can play around with this and you can run your data analysis using both methods. But at the end of the day, the actual values that are returned aren't going to be largely different if you have a sizable, an adequate sample. And ideally, we're not going to run this analysis anyways if we don't have an adequate sample size. So run principal component analysis and just go from there. And then if you have oddities in your data, you may try a common factor analysis, but you're probably going to be fine with a PCA. So now we want to talk about how to determine the number of factors. And there's going to be, this is going to take a little trial and error when you have your data set. So this is going to be something where you go back and forth looking at different options that are available to you. And again, we specify that in this area here where we're looking at the number of factors to extract or to analyze. There are three basic considerations here where we choose the number of factors that we want to consider. And again, this is an iterative process, so we're going to go back and forth probably looking at numbers of factors and the variables that we're going to use. So the latent root procedure or the latent root rule or the eigenvalue rule is the most popular approach here, sometimes called the Kaiser's rule, but it's really the eigenvalue greater than 1 rule. And so when you run your data analysis, it's going to pull out the commonalities, the variance of shared commonality, the shared variance of through commonalities across your variables. And when the total variance is calculated, then you'll get a list of a list of factors, if you will, or a list of factors, one for every variable you have. And so when you look at the total variance if it's something that's reported in its eigenvalue as greater than 1, then chances are it has enough strength, if you will, between variables to stand alone as its own factor. So there's going to be a table that's reported in your output that lists your eigenvalues for each possible factor. And again, one for every variable you have. Only the factors that have an eigenvalue greater than 1 is selected if you use the latent root criterion, or if you want to call it the eigenvalue greater than 1 rule or the Kaiser rule. Okay, so this is probably the most commonly referred to rule to help you determine how many factors to use. So eigenvalue greater than 1 is what you want to think about. Number 2, it's something called the Scree test criterion. And basically what the Scree test is a graphical description or a graphical plotting of your eigenvalues. So if you take your latent root criterion, if you take the eigenvalues chart there, what it'll do, the Scree test will just produce a chart that has a depiction of your eigenvalues. And basically what you do is you look for a slant in the chart, and then where the chart flattens out, that's your cutoff point. That's your cutoff point in terms of how to determine the number of factors that you should use. Okay, so that would be a second approach. It's a visual approach that takes some interpretation in order to perform. The third thing that you want to look at is just simply thinking about the questions you've asked and theoretically trying to determine which ones would naturally go together. So you've got all these variables and you've written out these variables. They're probably coming from a survey, and in advance you probably have an idea of which ones should go together and how many factors you should have. So a good researcher will in advance plan their survey in such a way where they will be able to predict how many factors they'll have in advance, and so that should obviously imply how many factors you'll choose here. And if you end up using a different number of factors in your analysis than what you originally planned in your research instrument, then that's actually oftentimes an interesting finding, or it indicates that you made a mistake or a problem somewhere along in your research. So if you have, like, for instance, multiple factors that don't really go with the data that you suggest, then maybe you collected the data wrong, or maybe there's a problem with your research instrument that you need to investigate further. Okay, so these three rules are typically used, these methods of determining how many factors you should use. The latent factor rule is probably the most common. Okay, so as you're looking at your variables, the first factor that you find, or you're looking at your eigenvalues, the first factor that is reported will have the largest eigenvalue. Each subsequent factor will have a smaller and smaller eigenvalue. Factors with eigenvalues greater than 1 are the ones we often want to keep. Those are the ones we typically look to first. We evaluate the Scree plot, is what it's called, to do the Scree test. So we look at that. Oftentimes with the Scree test, we will often have, or sometimes have, more factors, and we may have some factors that are less than 1. So that would give you a little bit more flexibility. Keep in mind 2 factors, though. You can't have too few factors, because if you have too few factors that have lots of variables loaded on them, you're probably missing some detail in your data, in the structure of your data. So you want to have meaningful factors and enough of them, but you also can't have too many factors. So too many factors would mean you're not specifying your data well enough. Too few factors would mean you're missing out on a lot of detail and structure of your data that you want to be able to identify. Another rule here that's not necessarily listed is that for every factor, generally speaking, now this is not 100% of the time, but generally speaking, you want to have at least 3 variables that would load onto each factor. Okay, so that means that for each factor that you generally want to have at least 3 variables that would load onto it and reflect the underlying factor that you have determined. So if you have some factors that are returned that you're looking at that don't have 3 variables, you might consider dropping those, because and then that would affect the number of factors that you have overall. Okay, so this has been a quick discussion then on determining which factors to retain, and or actually, how many factors you should actually call for, and then the method that you would use in order to statistically derive your factors.